What's up, coders? Welcome back to another episode of Conquering the JavaScript Interview. Today, we're going to be dividing and conquering our way through the quicksort algorithm. I promise it's going to be pivotal in your understanding of these sorting algorithms. So as quick as a flash, we're going to be zooming through our unsorted problems and leaving them in the dust. So it's time to get in the fast lane with quicksort. Like I'd mentioned in my previous sorting algorithm videos, these are more of a conceptual thing you should be understanding and a little bit less of can I memorize how to code one. So keep that in mind. This one's going to be a little bit more complex than the other three I have done thus far, which I'll try to remember and include in the description and links in the description down below, which are bubble sort, selection sort, and insertion sort. Those are fairly simple to understand and go through, and this is where we're going to begin hitting some more complex ones. We'll be using recursion and a left and right kind of pointer style system to try and divide and conquer, like the pun in the introduction alluded to. So let's first talk about a possible analogy to tackle this one mentally before we begin writing the code out, because I promise the code is a little bit gnarlier than normal. It makes sense when you understand what all these terms are, which is how most things work. Am I right? And what am I saying over here? So imagine, again, we're our librarians. Our goal is we have a bookshelf. It has various books on it that are of varying heights, and our goal is to sort those varying height books to get an ascending height bookshelf, right? That's the whole purpose here. Just like everything else, except at this time, we're using the quick sort approach. We start by selecting a book. We're going to make the assumption that we're going to pick the first book on the shelf. That's it. We're going to pick the first book, and we're going to call this our pivot book. So whenever I say the term pivot, just know it's our element, in our case, book, we have just arbitrarily or mathematically somehow have chosen as our reference book. So when I say a pivot book or pivot element or just pivot, that is our selected book we are currently looking at. The goal of the pivot is we want to move things around it so it is then theoretically in its sorted position without actually being quote unquote moved. We just move things around it. So that's our reference book for this round of sorting. The height of the book is going to split our task into smaller tasks, subtasks. So we proceed moving from left to right on our bookshelf. We have our pivot book, right? And what we're doing is we ask ourselves, is the next book we're looking at, right, taller or shorter than our pivot book? If it is shorter, we're going to move it or swap it to the left-hand side. While we're doing that, we're also going to keep track how many things we swap around our pivot book. We're going to call that a swap index. So we have our pivot book. We're just comparing every book on the bookshelf. Is it taller? Leave it there. Is it shorter? Move it to the left. So this process of moving shorters to the left, tallers to the right around our pivot book means that once we are done iterating through the entire array, we have our pivot book where it should be, with all things smaller to the left, all things smaller to the right. And after that, our pivot book is in its sorted position, because that's where it should be. We've also, like I said, every time we've swapped a shorter book to the left-hand side, we have kept track of how many swaps. That is our swap index, because that's how many spaces forward or to the right our pivot has moved. And if we know that, we can then divide around that pivot and say, shorter to the left, taller to the right. Repeat the process to the right-hand side, repeat the process to the left-hand side, which will subsection that, and each of those subsections will get subsectioned until we eventually arrive at our entirely sorted array. That's what the whole recursive thing is, right? So like I said, once we have our pivot correctly sorted, we count how many swaps happened, which means we have where our two subsections are. Everything before that is our new quicksort. Everything to the right of that is our other quicksort, and we just keep on quicksorting each smaller and smaller subsection. Once our quicksort has a subsection that's only one book long, we have an entirely sorted array of books. So that sounds kind of complicated. Let's break down a couple things. Remember our pivot selection. There's actually a couple different ways you could select a pivot book. For simplicity in this video, I want to choose to just select our pivot as the first book we encounter in any given section, whether that is our entire array at the first iteration, or our first tallest book after our first pivot, or our potentially second shortest book at our other subsection, right? So like the whole point is I'm just going to select the first element in our new subsection every single time. Partitioning. That is what I meant by every single time we move our pivot until it's in its correct position, and then we have our two subsections. That is our partitioned, right? We have a left-hand side and a right-hand side, and that's going to keep on occurring over and over and over again. That's where the recursion happens. That subsectioning around a correctly sorted pivot, that's the recursive property of the quicksort algorithm. We're going to call the quicksort from within itself to find a pivot, move things around, give us that new index of where the pivot moved to, and then boom, we have two more smaller subsections. So it's going to be just like quickly crazy branching, diverting tree as recursive divide and conquer strategy, like the pun at the beginning of the video, said. Then that whole process will continue, and every book will be in its correct place on the shelf, because eventually it'll come down to a singular pivot with nothing to move to its left-hand side, which means we are now left with a completely sorted array. And just like that, our librarian's job is done. So I think I can help this one by actually visualizing this, not just through an analogy, but through actually taking this input array and trying to quicksort it with what we have learned, and possibly with some screen drawing as well. So hopefully this is zoomed in enough. I ran into some issues on other attempts to record this, where if I draw something with a pen on the screen, if I scroll down, obviously it's not going to work. So that is our input array that we are looking at here together. Like I had said, we're going to assume that our first time pivoting, 64 is going to be our pivot number. I'm going to make the assumption, pull the first book out, that's our pivot. That gives us an array of the following. So yeah, I'll do something like this. So that'll now give us an array that looks like this. Is 34 less than 64? It is. Is 25 less? Yes, it is. Is 12 less? Yes, it is. Is 22 yes? Yes, it is. Is 11 less? Yes, it is. Then we have 64 and 90 because 90 stayed where it was. So on our first iteration, our pivot is 64. We compare that. We move all things smaller to the left, leave all things taller to the right. Okay. Now, we have two new subsections to look at in this one, and we're going to imagine we can put two dividing lines right here on our bookshelf. Everything to the left is a new subsection. The pivot is one section because it is... I just realized I didn't select the right view. There we go. Hashtag professional. Everything to the left-hand side of that subsection is the shorter books. In between the two sections is the correctly sorted pivot book. Everything to the right is larger. Now, because we have no other elements to sort through, we have one book, we know that the right hand would finish here saying, oh, I only have one book left, which means I'm a correctly sorted book. Now, the process on the left-hand side is going to repeat in the exact same fashion. We're like, okay, our new pivot for the left-hand subarray is now 34. I'm just going to assume it's the first book. 34, if that's our pivot, here's where we wind up with our new array. Is 25 less than 34? Yes, it is. Is 12 less than 34? Yes, it is. 22 and 11 are all less than 34, and our current subsections are already correctly done. This means that once I have that done, this is our original. This is our right-hand side that was also completed. Now we have this new completion right here, right, where we have 34 is correctly pivoted, and we have nothing to the right-hand side anymore, but we do have some more to the left-hand side, which means I can now come down here and say our next pivot will be what? 25 in this array we're looking at, which means is 12 less, is 22 less, is 11 less, leaving us with 25, 34, 64, and 90. And hopefully it's starting to make sense. I'll stop sub-bracketing it as much. Our next pivot is 12, which means we are going to wind up with 11, 12, 22, 25, 34, 64, and 90. And let me go ahead and draw those in real quick. So like I had said, this was our first subsection. This was our right-hand and only right-hand subsection. This was our second left-hand subsection. This was our next subsection. And then finally, from there, we had our 12 subsection, right? So that's what ended up being there. And we only have one element left to sort, which means it must be our smallest. And we have ourselves a sorted array after several iterations here, and that's what we're doing here. So in this example, I didn't have anything on the right-hand side besides the 90, so there was no extra pivoting that we had to do on the right-hand side. But remember, if we did have more numbers that were larger than the original 64, like if we had 100 and 105, we would repeat the process in the same way on the right-hand side. That is the divide and conquer strategy this whole thing takes. So with that in mind, hopefully you have a better visual idea of what we're going to be attempting to do with this particular algorithm, and again, why I had to set up a little bit more work up front before we began actually writing out the code. So, because this thing is going to be recursive, we need to have some way of knowing when to exit the recursive problem. We need to provide additional arguments to our quicksort parameters in order for us to know what our subsections are and as they grow or shrink, rather. We need to know the original array, perfect argument right there. We also need to know a left-hand side and a right-hand side of whatever subsection we are dealing with. On the first call of this function, the left-hand side will obviously be 64, the 0, and the right-hand side will be the 90, which will be array length minus 1. Those are our function parameters, and the default values we need to provide to left and right to make sure that when we call quicksort the first time, we have our boundaries set up and ready to go. Now from here, we need to know how long do we sort for. So clearly some kind of logical condition needs to happen here. If there's more than one element in the segment to sort. Right, so if there's more than one element, now recall on our first after our first pivot and iterating on our input array, we wound up with a 90 on one hand side. So the left and right boundaries would be the same value, array length minus 1, which means there's no reason to pivot and sort anything because this is theoretically sorted. So long as left is less than right, meaning the left-hand indice or boundary of our subsection is less than the right-hand indice of our boundary of this subsection. But once they meet, that means we're out of things, or we have one thing left, which means there's nothing to sort because it's theoretically an already sorted position. From here, what we need to do is find a pivot, or find the pivot index by partitioning the array segment and moving smaller elements to the left, leaving bigger elements to the right, right? So in our case, we're only swapping smallest to the left-hand side of our pivot. So we also need to know, once we move our pivot over, for example, remember our input value of 64, our very first iteration, remember this as a visualizing tool. Our very first iteration means that this is what we got. And what happened was the 64 moved from index 0 to 0, 1, 2, 3, 4, 5. That means we have moved 5 elements that were smaller than our pivot to the left-hand side. That is what we need to track, and that's what we're going to call our swap index. That is what we need to tell our quicksort algorithm, hey, this is where our pivot is, and the boundaries on it, that new subsection we're dividing, will be to the left-hand side and to the right-hand side as needed. So we need to track how many, we have to first iterate and swap any elements we need to, and track how many we swapped. And then, ultimately, swap them all, right? That's what we have to do. We actually have to run all these swaps. And again, ultimately, I have to take the 64, which will be at index 0, and if I know I'm going to swap 5 things, I have to swap it on over to that correct position like that. So that's what's going to happen here, okay? Now, to do that, we can write the code here, but I'm going to choose to, and you'll see this online quite regularly, using a utility function, sometimes called pivot or swap and pivot or something like that. So we need to know, hey, where did our pivot move to after everything's been swapped? So we need to have some kind of function that takes, surprise, surprise, a couple of arguments to do its job. We're going to pass in the array, we're going to pass in our left-hand boundary and our right-hand boundary into our new pivot. That's what we're going to do. So our function called pivot will take very similar looking arguments. To save ourselves from calling it left and right, I'm going to say we're going to call it start and end in this case. Right? Now, just to play it safe, I'm also going to pass in default args to this one. I don't think we need to, because if I call it with left and right, which will be 0 and array length minus 1, pass in as left and right on the initial call, I'm going to play it safe and just add these here, and we can always just test to remove them at the end here. I don't think that will cause any kind of issues, but I'm going to not risk it. So yeah, we're going to pass in a start value and an end value, and we're going to pick a pivot point. What pivot point are we picking? Again, the first element. So that would be, let our pivot be whatever our array, the element is at the start of our array. We arbitrarily, there's no typo here, I don't think. We arbitrarily pick our first element in this partition as the pivot. Remember, we picked 64 as the first pivot, just arbitrarily. And from there, you saw we picked 34, and et cetera, until we wound up with our array. So we just picked the first thing. Also, we need to know where our swap index begins. Whether that's in our left-hand array or our right-hand array, we got to know where it starts. And it is going to be wherever we start at this particular position. So the 0 will come from this 64, this 0th index position on the left-hand side, and will continue to be whatever, probably 0 as we keep looping through this. But it would be like 7 or 8 or 9 on this hand side if there were more numbers on this array. Like again, if there were more numbers to be sorted here, then after that initial pivot where 64 winds up in here, then the start position will be 90 and onwards as our start, which is why we have to keep that in track. We got to keep track of both the left and the right-hand sides of our chosen approach, right? So that's what start represents. The starting point on the smaller section of books, the starting point on the larger section of books once we partition into two. From there, like I had mentioned, what do we comment this as? We'll say, it's initializing the start index as a swap index. That's where it begins. Now we're going to keep track of how many things we swap. To do that, we're going to move through the array one element at a time. Are we going to start at 0? No. We're going to start at whatever start we have passed in. So that's going to be start plus 1. Why is it plus 1? Well, if our pivot is 64, we do not take 64 to compare against 64 itself. We go start plus 1 to get 34, hence why we get starting at that position. We're going to continue until we get to the end of this array, or the end of this section, right? And we're going to move one book at a time. So basically, for each element of our partition, except for our pivot. For each element of this partition, except the pivot. We need to do the following. Make a condition. If the element is smaller than the pivot. Remember, that is our prime question. If our element we're looking at is smaller than our pivot, we swap and also say, hey, our swap index moved up 1. So I will say, if the pivot is bigger than our element, right? Or if the element is smaller than our pivot, it is time to say, hey, we're about to move an element over, so the swap index of our pivot's going to move up eventually, right? Because we have to keep track of how many things we're swapping. That's what that represents. Then we actually have to do a swap element with element at swap index. So what we're going to do is say the following. We're going to do a ES6 array destructure swap, which you see me do in previous videos. This is also the same way you would just use a temporary variable to swap two element positions in an array. And you could do this with that temporary variable and 3 more lines, or this one line right here. So we're going to say, I want to take the current element we're looking at, the element at the swap index, and I wish to swap their respective positions like this. So remember, all this does is take the array, the element we're looking at, and swaps it with the element of the swap index, which means the element of the swap index becomes the element where we were originally looking at. So again, this is just the swapping of them and incrementing the swap index to count. Now, outside of this, we are Dunyan rings. This should move through the whole thing and swap all things to the left. And then finally, after all smaller things than our pivot have been swapped to the left, we have to swap the pivot element with the element at the swap index, right? So again, that 64 needs to swap to the swap index with whatever element's there. That way, we have our boundaries set. That 64 pivot book, we know its new position. Remember, that was when I said that we had to track where it went to. It went from the 0th position to 0, 1, 2, 3, 4, 5, right? So 5, not 6. It went to the 5th index position, and that's what we're tracking here, and that's what we're moving 64 to make sure that our boundaries around 64, those two partitions, are now set. So to do this, we're going to do another ES6 array destructured swap. We're going to say, take the current element. No, take the element of the swap index and move it. The pivot element. Oh my goodness, why am I losing my mind? Okay, we swap the pivot element with the element at the swap index. That'd be the pivot array start, right? With the swap index. And then we have to take what was at the swap index and move it to where our pivot was, like that. So that's why we end up with that value here. That's what we're doing here. Yeah. So swap index goes to start goes to swap index. That is what this comment is supposed to be telling me to remind me how to write this. Again, it gets confusing, doesn't it? So swap the pivot element with the element at the swap index, right? The pivot element with the element at the swap index. Okay. After that's done, we need to tell our code to return the swap index, which is what this code gets us right here. This says, hey, the 64 we're looking at here is now correctly set, which is why, come on, there we go, which is why we need to do that so we know where it got moved to. That is our pivot index that we are returning, which means we now have our subsection to the left of here, which is our pivot index -1, and to the right, which would be our pivot index +1. And those are our two new subsections that I must recursively ask Quicksort to do the same process on, right? That is what we're doing here. That is why, after we call this pivot index right here, I need to recursively sort the segment left of pivot. This is done by calling Quicksort with the array, our current left-hand boundary, and what our right-hand boundary will be what the pivot index was, -1. So that -1 comes into play. Remember, our new right-hand boundary is -1, left is still 0. That's that new subsection. Then, you guessed it, folks, recursively move to the right of the pivot. This would be whatever our right-hand boundary was, which would be the end of the array, and our new left-hand boundary will be our pivot, or our swap index, our pivot index +1. That's where the -1 and +1 from what I just drew a moment ago comes into play. That's what we're looking at here, okay? And then after all is said and done, we just need to return our sorted array. And guess what? Pretty sure that's it, unless I mess something up. Which there's a high possibility there's a typo here, which would be embarrassing in a lesson. But, I mean, that's coding, right? So let's see if we got this working the way we expected. Yeah. So yeah, let's try calling it with our input array right here and console logging the output and praying to Zeus himself to see if he's listening. 11, 12, 22, 25, 34, 64, 90. So yeah, that is our code. It's a fun one. I know it's a bit of a doozy as well in terms of like looking at the code here. So, you know, you can always rewatch this video, rewind as needed. Let me go ahead and remove the comments so we could kind of see the code not with so much space in between all the lines. I think that might help some of y'all as well. So again, there we go. There's that part. There's that part. Move that down. Yeah. We understand anytime we see those crazy sets of array brackets, we know those are just swapping index or swapping element array index positions. That's all we know that's happening there. And trying to like focus this down so we can see it in a tighter view, right? So yeah, there's Quicksort. So long as we have left and right hand boundaries to keep going between, we're going to pick a pivot, the starting book, and then swap things around, pivot, 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 move that pivot over until it's balanced where things to the left hand are smaller, things to the right hand are bigger, get that pivot index, and then with our new pivot index, -1 to the left, sort again, quick sort again, +1 to the right, quick sort again, and keep on subdividing and subdividing and subdividing until we have nothing left to quick sort, in which case we are returning our cleaned up array. So that's how we are dividing and conquering across this array to get all this information done. Our pivot utility function's purpose is to arbitrarily pick a pivot point or mathematically choose one, because there are better ways to do this. We simply are choosing whatever our starting index is, which could be +1 of our pivot, right? Or 0 in this case. So in that case, we iterate through every single book on our shelf. And if it's smaller than our pivot, we count a swap that's going to happen, and we swap those elements. Then from there, we take our element, our pivot, move it to how many swaps we made. So we take that 64 and move it to the end. That's what we do there. Or move it to the end of its section and call it done. And that done pivot swap, that done pivot index is what this value represents, which we get right here after calling it, and gives us our left-hand boundary and our right-hand boundary to go from there, which represents those pink lines I was drawing earlier on the screen. Now, this one's, like I said, fairly complicated, so hopefully y'all have followed along. Let's see, what else I cover here? I mean, before I talk about big O and stuff and whatnot, let's actually go and try and visualize this if at all possible. So I should have our good friend Timo Bingmann's visualizer here. So this is our unsorted bookshelf, and you can see in their case, it looks like they are picking a pivot in the middle and not at the very beginning. That is a difference here in this visualizer. Notice they pick the middle, which is a strategy you can do. You can take the length of your subsection, divide by 2, and pick that middle part. Again, there are pros and cons to picking a random pivot, one at the beginning, one in the middle, or some kind of or median, or some kind of combination, right? So there are different ways to compute a better pivot than just saying, I'll pick the first one. So here they pick the middle. Let's watch. You can see the divide and conquer happening. All things smaller get moved to the left, right? There's another chosen pivot. All things smaller go to the left, right? I don't know, I'm watching the recording when it's right in front of me. And then as you can see, this is much faster and more efficient than the other videos we have watched. So remember, it's picking a pivot, moving all things smaller to the left, all things taller to the right. Pick a pivot, all things smaller to the left, all things smaller to the right. And it's doing that in smaller and smaller and smaller subsections until we are left with an entirely sorted array. So while this visual isn't exactly what we've been doing, remember, theirs is picking a middle point rather than the beginning, but the overall logic is the same. If you find a video that does a beginning element pivot, please link it in the description, or not description, please link it in the comments down below, and I'll make sure to pin y'all and give you some credit for giving me a hand there as well. So that's the visual of what's going on here, and I guess for some breakdowns of some final pieces, right? So the reason this one is, the reason this one's very cool to know is that, again, recursion makes you look like a badass. It makes you look cool if you know how to use it properly and not break stuff. We are talking a big O best case time complexity of n log n, which is way better than our quadratics that are n squareds that we were getting in the previous 3 algorithms. This one occurs when the pivot element is always the median of the array, leading to a perfect split of the array into 2 equal halves at each level. That's chef's kiss. Our average case. This is a big O time we're talking about here, because again, these have more considerations than just this is it all the time, boom, roasted. Average case will also be an O log n in terms of the average, and at worst, unfortunately, it can lead to an n squared worst case scenario, right? So in the average scenario, quicksort always performs pretty dang well, which is why it's preferred for large data sets. So unlike the other ones where I said it's great for small data sets or already partially sorted data sets, this one's great for long data sets. Worst case, again, this occurs when the pivot element is either the smallest or the largest. So like if I found the smallest element by happenstance the first time, I'm going to have to do... It'll lead to a very unbalanced partition, and that will require more and more and more and more recursive calls to eventually figure out that, oh, that was the smallest element, right? So if 90 was the first element, or like if the smallest element was 11 first off, that would lead to an unbalanced partition and make me recursively call this more and more before it gets sorted out, right? So this is actually considered kind of rare in practice for this algorithm, especially if you choose the pivot element randomly, then you just got really unlucky if the random choice of a pivot happened to be the smallest or largest thing of the array already. In terms of space complexity, there are other solutions. You might see another solution online that has something that looks like this as an answer, right? Something akin to this. That ends up getting us a space complexity that is that's worse because it ends up requiring other sub-arrays that grow in size as well, which makes variables. So if you see that kind of solution, it is easier to see and understand and read than this one, but it does have worse big O space. So in terms of space complexity, we have a big O of just log n. I'm fairly certain on this one. It's because it needs space for recursion. So remember, recursion adds to the JavaScript call stack. So as many times as these are called, it keeps adding to the call stack, which takes some amount of space, which is a log of n, right? So just depending on how many times we have to keep on dividing our subarrays and subarrays and subarrays to quicksort, yeah, that's going to be our average space complexity for this problem, right? But again, if you get like really bad pivots, like the smallest or largest elements, it could go as bad as big O of just n, which is that linear line. But again, that's exceedingly rare for that to happen. Kind of like I said, this is just really, really bad luck on a bad chosen pivot or something like that. In terms of trying to visualize that, let's remind ourselves what these things look like if you're your first time here. Big O of log of, again, on average, n log n. We already see that's better than our quadratic for selection, insert, and bubble sorts. So best case and average case scenario, we already have a more efficient algorithm. In terms of space, remember the recursion call stack gets worse and worse. We have to keep on stacking quicksort on quicksort on quicksort on quicksort. So our call stack grows in terms of space, which is a log of n, which you can see is not terrible depending on how much the call stack has to get called. But again, if we end up with extraordinarily bad pivots and extraordinarily bad partitions, at worst it can go to this linear line of n. So yeah, pros and cons, right? This is our most efficient one, right? Especially for large data sets. The other ones I said were good. This one is excellent in terms of efficiency for large data sets. It also, like the others, does in-place sorting, right? There means no additional storage space other than the recursive calls needs to happen, right? This one also, due to the divide and conquer approach it takes, has a better cache performance as it effectively works on smaller and smaller parts of the original array. It can make it faster in practice compared to other sorting algorithms. And again, it's incredibly versatile. This can be done on tons of data sets, not just numbers. It can be done on objects and strings and tons of other things where the other algorithms do have the limitations of being more oriented towards numbers and things like that. But again, worst case scenario, you can wind up with an equally bad time complexity. So that's a con for quicksort. It is not stable. It is not a stable sorting algorithm. So if you have similar values, they may not wind up in the same place. Watch the previous video, Insertion Sort, for a quick breakdown on what stability is. It means if we have object keys that are different with similar values, the similar values and keys may not be in the correct order. Like we may lose key order if we have values that are the same. And again, recursion can be a Stack Overflow problem for insanely large data sets. If you have to call the quicksort on recursive too many times, it could break the call stack, right? Stack Overflow, that's where the name comes from. So that could be a problem on insanely large data sets. So yeah, in terms of selecting a pivot, we selected just the start one here, the first element as a pivot. That's what we did right here. It's simple, but it can suffer from poor performance, right? So again, last element is the same thing, similar downsides as taking the first one. Taking a random one, so generating a random number between the start and the end using a math.random logic to choose something randomly between the start and the end is a valid strategy. It also helps avoid that worst case scenario that we might start with the tallest or the smallest book or element by default. And there's also one called in my notes here, median of 3, which in that method, you in the median, the first, middle, and last elements of the array is chosen as the pivot method, and it's the most balanced way to create partitions, right? But that one's way more complex in the scope of this. Just know that there are different strategies to choosing your pivot that could affect your performance. So unlike the rest of them, they're all cool, but this one actually has coolness on top of it, right? Very efficient, in-place sorting, divide and conquer, universality. It's great for multiple kinds of data sets. It really deepens your understanding of recursion, which is a great tool to have in that tool belt of yours. And some insights into pivot selection could set you apart from an interviewee who's like, I mean, I guess there's some logic pivot selecting. I don't know. I didn't really look into it. Well, you did because you watched this video. So you know that even though this is the simplest way to begin to understand it, that there are other ways to choose the pivot that can make your life easier and the algorithm more efficient, right? So I think I need to do like a TLDR video on its own where I compare and contrast all these things. So remember, in terms of bubble sort, quick sort beats it in efficiency. They both are in-place algorithms. Bubble sort is stable, though. So if you need stability on object keys and value pairs, right? Stability might be an important thing for you, in which case wouldn't choose quick sort. Versus selection, quick sort beats it again. They're both in place. And selection sort isn't stable. So honestly, just pick quick sort instead of selection ever. Selection is one you just learn for fun. And then quick sort versus insertion. Efficiency-wise, this one beats it. They are both in place. However, insertion sort does maintain stability. So I would do insertion if you need stability and quick sort if you don't. That would be my binary logic tree, right? So that was a lot of code and a lot of talking. And this is a complex one, y'all. So if you have to watch this more than once, if you all want any additional details, please comment down below and I'll be happy to link any additional, or not link, I'll link or make additional content to explain this one further. But again, thank you all for watching. I hope you found it helpful in our journey together, becoming better developers. If you like this video, give it a thumbs up and consider subscribing to the channel for more videos like this. Remember, constructive and positive comments are always welcome here. And let's keep this discussion going. Help each other improve, right? That's what it's all about. So thanks again for tuning in, and I'll see y'all in the next video. Remember, this is the Monato's Power.